I've been doing film photography since I was a kid. While everyone else was switching to digital, I kept going backwards. And eventually I found myself making photographs the same way people did more than 170 years ago. But today we're going to do something the inventors of photography could never have imagined. We're going to take this photograph and put it inside a scanning electron microscope. But before we make a wet plate selfie, I want to show you a different side of film photography. Not the usual film photography YouTuber side. Today we're going to explore 3 analog photography challenges through the eyes of the scanning electron microscope, because an electron microscope doesn't just magnify things, it changes the questions you can ask. Chapter 1: Pinhole photography. No lens, no focusing mechanism, just geometry, physics and light. I designed this camera for 4x5 cassettes and SolidWorks, and it was 3D printed by my friend. This one is literally made from cardboard. Honestly, you can build a pinhole camera out of almost anything. Apple product boxes make surprisingly good cameras. The physics is beautifully simple. Light travels through a tiny opening and projects an inverted image onto the film. No lens required. Infinite depth of field. No perspective distortion. The world as it is. Now, the aperture is where things get interesting. This one was laser drilled. I bought it years ago on eBay. This one I made myself with a sewing needle and an old 35mm film canister. You could even make one from an aluminum soda can. Let's see what they actually look like under the microscope. Okay, now the difference becomes obvious. The laser-drilled aperture is almost perfectly circular. The edges are incredibly smooth. The metal was melted and shaped by a focused laser beam. The foil itself is only about 10 micrometers thick. If the foil will be thicker, there will be tons of parasite refractions inside this cylinder hole. Now compare that with my homemade version. Alright, it definitely a hole and it works, but the edges are rough. The hole isn't perfectly round, and those tiny imperfections scatter light before it even reaches the film. If you're shooting large negatives, you probably won't notice much difference, but with smaller formats every imperfection matters. And the optimal size of the aperture for the large 8x10 negatives is much bigger than for 4x5s or medium format films. So yes, if you want incredibly fine details, I recommend to find a nice laser-drilled pinhole. Interestingly, the same idea appears in confocal microscopy. There, a pinhole blocks all the out-of-focus light, allowing only the sharply focused rays to reach the detector. More scientific, more delicate, and definitely more expensive. Different instrument with exactly the same optical principle. Of course, there's a limit. Make the hole too small and diffraction begins to dominate. The light spreads around the edges and sharpness starts disappearing again. There are a bunch of apps that can help you calculate the optimal diameter for the focal length of your box. Pinhole photography has always felt timeless to me. Nothing between the scene and the film, except a tiny hole, long exposures and infinite depth of field. Chapter 2: Trichrome photography. Making color photographs on black and white film. Color photography is actually much older than color film. Let me show you what I mean. All you need is 3 black and white photographs. One through a red filter, one through a green filter, and one through a blue. Each filter absorbs a different amount of light, so every exposure has to be adjusted individually. We can set up the scene. The wind will be another challenge. I think that the branches of the tree will be suspicious in the final image. Anyway, 3 frames with different filters. Normal processing. After developing the film, I scan all 3 negatives, invert them and combine them digitally. Red becomes the red channel, green becomes green and blue becomes blue. Together they recreate the full color image. In fact, only the branches make it clear that this is not an ordinary color photo. This is not a modern trick. Sergei Prokudin-Gorsky was doing exactly this over a century ago. He wasn't the first who used this technique, but his photographs remain some of the finest examples of early color photography ever made. His photographs never existed as color prints. The color image existed only as simultaneous projection of three black and white glass positives through red, green and blue filters. He even made what might be one of the earliest color selfies ever taken. 1912. Just wow. The fascinating part is that many scientific instruments still work exactly the same way. Monochrome sensors, beam splitters and prisms separating wavelength. Even this Fuji Frontier film scanner captures color by recording separate monochrome channels before combining them into a final image. The same principle appears everywhere. Do you remember this 3CCD label on the vintage camcorders? When people think about film, they usually think about grain. Tiny metallic silver particles suspended inside gelatin. So let's actually look at them. Under the optical microscope, the film is transparent enough that the silver grains appear as dark structures inside the emulsion. Now the electron microscope. But first, a thin conductive coating. This helps prevent the sample from charging under the electron beam. Into the SCM and nothing. At least not what we expected. We're using one of the most powerful imaging tools ever built, and yet it can't reveal something that's easily visible with an ordinary optical microscope. That's actually fascinating, because what we're seeing is not a film grain, it's only the surface of the gelatin. So I cut the sample at a 45-degree angle to expose the cross-section. This electron microscope can operate in two different imaging modes: secondary electrons and backscattered electrons. Secondary electrons come only from the very surface of the sample, producing highly detailed images of its topography. Backscattered electrons are different. They originate from a much larger interaction volume beneath the surface, whose depth depends on the accelerating voltage and the material itself. This gives us compositional contrast. Materials with a high atomic number appear brighter, while the plastic remains dark. For this sample, that's exactly what we need. Now we can clearly see the film grain and emulsion layer. It's just beneath the surface. Chapter 3. A wet plate selfie. Now for the holy grail of historical photography. A photo made on a freshly prepared wet plate. Let's prepare everything. Here's a vertical silver nitrate bath. And this is salted collodion containing potassium iodide and cadmium bromide. I'm also preparing the developer. It's a simple ferrous sulfate solution. Once the plate is sensitized, every second counts. The process itself is surprisingly straightforward, although it does take a bit of practice. First, I pour the collodion onto a clean tin plate. It spreads into a thin, transparent film that holds the salts in place. In many ways, it serves the same purpose as gelatin in modern photographic film. Next, the plate goes into the silver nitrate bath for about 4 minutes. Inside the silver nitrate bath, the dissolved salts react to form light-sensitive silver iodide and silver bromide. At this point, the plate becomes sensitive to light. Red light doesn't have enough energy to significantly expose silver halides, so the rest of the process happens under safe light conditions. I'm using a vintage Graflex camera along with a ridiculous 6-meter pneumatic cable release. While the plate is being sensitized, I finish set up the shot. Wet plate collodion is incredibly slow. Its sensitivity depends heavily on ultraviolet light. Bright sunlight makes a huge difference. In open shade, I'm expecting an exposure of about 6 seconds with wide open aperture. The wet plate goes into the holder. Now everything has to happen before the collodion dries. Once it dries, the chemistry stops and the carriage turns back into a pumpkin. Time for the exposure. Let's be fair. Making a wet plate selfie while filming yourself making a wet plate selfie turns out to be more challenging than I expected. After exposure, the developer reduces the exposed silver halides to metallic silver, while the fixer removes everything that was not exposed. As the fixer dissolves the unexposed silver halides, the finished image slowly appears. And there it is. I'm actually quite happy with the result. Holding perfectly still for 6 seconds is not easy, although my sneakers came out just perfect. Modern sneakers and 19th century photography make a surprisingly good combination. But this is the part I've been waiting for. Let's find out what a wet plate photo looks like inside the scanning electron microscope. Once again, let's cover the plate with just a few nanometers conductive coating, and we're ready to go. I've certainly never seen a Nike swoosh under a scanning electron microscope before. These tiny silver particles are only about 1 micrometer across, and yet together they form an image nearly 4 by 5 inches in size. That's an astonishing amount of information packed into a single photograph. And that's nowhere near the limit. With large format photography, you can go much bigger, much bigger. It's one of the reasons why even on group portraits made more than a century ago, you can often zoom in and still recognize every face. Not because of digital pixels, but because millions upon millions of microscopic silver particles recorded the light. A 19th century technology viewed through a 21st century microscope. I think that's pretty amazing. Sometimes the closer you look, the more impressive all technology becomes. If you haven't seen my video about quadraphonic vinyl, I'll leave it here. It's another retrospective look at a remarkably clever technology from the past. Thanks for watching, and I'll see you next time.